All right, good afternoon, everyone. Today I'm going to be talking to you a little bit more about color and light and everything awesome like that. Now, to start us off, we are going to be looking at the first problem on formative assessment 5.4. If you go in your packet, flip to the page this is on, and we're just going to talk a little bit more about this. Now, one thing I noticed is that in this problem, we forgot to tell you if we're talking about color by addition or color by subtraction. In this case, an indicator here, colors of light, we're going to talk about light emission, so color by addition. When we have color by addition, our primary colors are red, green, and blue. Those are the primary colors of light for things which output light. Now, we can mix those colors together to get other colors. That's going to be how all of our displays, all of our things that emit light, like our TVs, how they work. Now, in this case right here, we've mixed red and green light together. When we mix red and green, and this is the one that usually throws people a little bit, we get yellow. Again, when you're in person sometime, or just online, make sure you try that color shadow station, or just like the station with the colored flashlights. You are going to be able to see that it really does combine together to give you yellow. Now, when we go and we mix red and blue, that is going to give us magenta. Lastly, our blue and green gives me my favorite of the secondary colors, cyan. Now, the last thing we get is that if we mix together red and green and blue, we actually get white light. White light is kind of all of the colors glued together. There you go. I noticed this year over Zoom, a lot of people have those cool color-changing light strips in their rooms at home. This is the principle those operate off of, right? Those color-changing light strips that I saw a fair number of students have in their bedrooms at home or in their workspaces at home, well, those were a red LED, a green LED, and a blue LED in each little pixel there. And they just turn them on to different colors to give you all those different colors of light and make your room look awesome. All right, let's look at the next problem. So this next problem is a color by subtraction problem. We know it's color by subtraction because we're talking about filters, and filters are one of our color by subtraction examples. A good example of a color filter would be this, which I'm hoping it shows up on the screen, red cube. This red cube is it's a red filter. It only lets red light through. It's used on a machine I have to block other colors of light from the workspace, but in this case, it's also a good example of just this red filter right here. A red filter, much like a coffee filter, only allows through what's in the name. Coffee filter allows coffee through. Red filter allows red through. Blue and green don't make it because a red filter filters out those colors. Now the red light makes it to the blue filter. A blue filter only lets blue light through. So, bump, red light can't make it. And we aren't going to magically, this is a common misconception I see, we're not going to magically get blue light coming out of the blue filter. We blocked the blue light earlier, none made it through, so there's no blue light to pass through that blue filter. Now in the next problem, we're going to be trying to explain this to a second grader. Second graders don't drink coffee, which is, you know, it's a little bit hard. I like the coffee reference because that's just something I drink a lot of in my life. And I just don't know second graders that well. My kid's 9 months old. I don't really know what second graders are into. I'm going to pick an age inappropriate option and think about a car. And your car has an air filter. That air filter, right, is going to give your car clean air. And so, you know, if I'm going to explain this to someone who's maybe a little older than a second grader, yeah, you know what? I'm just sticking to my coffee analogy. Coffee filter? They probably know what coffee is. Coffee filter lets coffee through. It holds the grounds. and doesn't let them pass through. Gives you coffee. It only lets coffee through. Holds the grounds and anything else. Holds anything not coffee. I've tried this before. Some people like a little lavender in their coffee. I've tried putting a little bit of dried lavender in with my coffee grounds, right? And that lavender didn't make it through because it's not coffee. I don't know. That, to me, this is the explanation for a second grader. Coffee filter lets coffee through, holds the grounds, anything that's not coffee. Color filters let their color through. And then they block all else. All right. That's just what filters in general do. Filters filter out things that aren't what you want. See, it's kind of nice being online. I don't really need to leave the same wait time because, well, you can hit pause. As we move on to other ones here, we've got some information. We got white light. It's passing through the filter below on problem number 3. Now, we've been given some information here. We know that red, blue, and green light is heading towards the filter, i.e. white light. And now we have to identify what color this filter is, right? We have to fill in this box right here. And we know that this filter filtered out red, but allowed both blue light and green light through. Well, if we're letting blue light and green light through, we're kind of adding together the blue and the green. It's color by addition. And so you'll see on the other side, you're going to be like, oh, well, blue plus green, that gives us cyan. Again, one of my favorite secondary colors of light. In part because I really like blue and green. Red's a great color too. I just grew up loving the color blue. If the filtered light fell on an object containing yellow pigment, oh, what color would you see? Why? Well, we have to come back and look at this. Up here, we filtered out everything that wasn't cyan. So we have blue light and we have green light. And they are heading towards an object that contains yellow pigment. Now, not the best example of it, but here's this very dirty yellow rig is our object containing yellow pigment. This is only going to allow colors that are made up of yellow to reflect off of it. So here's our yellow rag. This yellow rag reflects the colors that make up yellow, so it reflects red, it reflects green light, and it absorbs blue light. So what that means is any blue light that hits this is going to get kind of absorbed by the cloth, eaten on up, and turned into heat. We're not going to experience that blue light. And so here, blue and green are coming towards this yellow object. The yellow object reflects the green, but the blue is trapped inside there and gets absorbed, and that energy just slowly and imperceptibly warms up our little yellow cloth here. You ever wondered why black shirts get so hot? They're absorbing a lot of energy. In this case, what color would we see? Green light. Now, this would be the why, right? Yellow pigments reflect red and green. They absorb blue. Blue and green light struck this yellow rag. The green part of that light was reflected. The blue part of that light was absorbed. There we go. I like this unit because colors are all around us. Everything around us. We very intentionally over history have worked hard as a civilization to get pigments and make things colorful because colors are awesome. Wah wah. This formatting got a little messed up. So just ignore the stamp right there and I'm just going to be honest, everyone. White light's passing through the filters below. There's no filters. There's nothing left on here. It all got cut off. So we're done right there. I'm sorry about that. Everybody misses something sometimes. Everybody makes a mistake here and there. I'm a big believer in that, and we clearly just did. I hope this was helpful, and I hope you have a great rest of your day. Oh, trust me, the video is over. If you're still letting it play, it's just awkward now.